At 8 a.m.
At 8 a.m.?
Yeah, I'm going to lure you in early. I'm going to provide breakfast starting at 7. Good bagels at 7. Okay bagels at 7:30. All right, so I want to show you. Can we get going because class is shorter today? Only by like 5 minutes, but still. All right, so I want to show you the difference between area in polar and area in rectangular coordinates, which are like normal coordinates. When we normally do area, we normally think about the graph kind of sweeping out from left to right, kind of doing those rectangles from Riemann sums. We're definitely thinking like integrating along the x-axis or along the y-axis if you're feeling spicy. That is not how polar area works. I'm going to press play in a second. The angle we are going to be using as our variable of integration is theta. So the angle of our kind of point is going to be changing, which means we're not working with rectangles anymore, which is why this is going to be a little bit weird. So notice as I press play on this, we sweep out area as the angle changes. So it's going to be a little bit different as we try to find this area because we're not going to be working with just our function as the integrand. So one thing you'll notice today is we're never just going to put whatever r equals in an integral and call it a day. There's going to be some extra stuff going on. You may also notice that the angles are going to be very important for our bounds. So we're going to spend, honestly, most of our time today talking about how to find the bounds for our integral. Ready? We're going to start easy and get harder, as is tradition. All right, have you guys heard of the word sector before? Anyone know what it is? Yes, a portion of a circle. So if you imagine pizzas are circles, a sector is like a pizza slice. So this is the center of the circle. I'm calling this angle theta. And then the side will be the radius. So we got theta and r. Why am I talking about all of this? Because all of our polar stuff is in terms of theta and r. So how do we find the area of said pizza slice? We're going to take what proportion of the circle it is and multiply it by the area of the circle. So how much like angle is in a full circle? So if I want to start here and go all the way around in radians, 2 pi. Degrees are for dweebs. Or people who want to actually make sense of angles, but that's fine. All right, and this proportion, the angle that's in this sector, is theta. So we've got theta out of the 2 pi of the whole circle. A little bit of an easier question. What's the area formula for a circle? Pi r squared. All right, anything convenient you guys are noticing about what I wrote down? Let's get rid of those pi's. All right, so I'm going to write this kind of simplified. I'm going to, instead of dividing by 2, just write it as a 1/2. I've got my theta and my r squared. Now, like I said, we are going to be integrating in terms of theta, which means the end of my integral is going to have a d theta on it. So I'm going to kind of just move this around a little bit. I'm going to have 1/2 r squared. And then this theta is the thing that's getting kind of shrunk down. So if you think about the rectangles from Riemann sums, we were doing an x distance times a y distance, but we shoved that x into that dx at the end of the integral because we were making the rectangle really, 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 really skinny. In this case, we are shrinking that angle down a lot. So this is what our integrand is going to look like, and this is going to turn into d theta as we go towards our integral. So you can kind of, I like this picture. It's a little confusing, but I like this picture because it gets kind of that Riemann sum to integral idea out of here. So when we sweep out area, we're kind of sweeping out this way. We're going to go kind of like the unit circle you would think of, building it out like that. And we will start at an angle, stop at an angle, and we will be talking about sectors. So that 1/2 r squared is going to be in every single integral we do today. So if we were going to write down our integration formula, we're going from theta equals a to theta equals b. And we're going to do 1/2 r squared d theta. Again, the d theta is coming from the fact that we're adding up a bunch of these little skinny little pizza slices, integrating that so we get our area. So just like last time, I've kind of perused the last few years of AP questions, and we're going to do some of the select ones. So this first question is a real question off of an AP test. You may recognize that function. We worked with it last time when we were working with some of our analysis of the radius stuff. Here we have that, and they gave us a picture of what it looks like. Cool. So we want to find the area of this. This is actually one of the most straightforward questions I've ever seen on a polar one. So am I just, well, let's start here. What do you think the bounds are? Yeah, I'm going to go 0 to square root of pi. They gave them to me. They told me how much angle I need to make that shape. So I'm going to use it. Now, am I just going to put this function in my integrand, call it a day, be done? No. What am I going to put in there? All right, 1/2 r squared. All right. The only step I have left to do, since it says find the area, is chuck this into my calculator. Literally it. It is a weird function though, so let's see if we can all do it. Once you plug into your calculator, it does not matter what letter you have in your question. So if you have your calculator in just regular mode, you can use X's. We're going to talk about polar mode today so we can grab some pictures. But let's try to get everyone plugging this into the calculator, check and see if that area makes sense.
The difference between like squared on the side.
For this one, yes, because if I put the squared in here, I would only square the side versus squaring this part as well. Is that what you were asking?
The second part is side.
This guy?
Yeah. I put it outside.
On the calculator, I think if you put it outside, it's going to try to square the sine instead of the theta.
Oh, it's just
so you want to make sure that the theta is squared and then you're applying sine to it. So it depends on how you're writing it.
So it's like angle squared versus function squared.
Exactly. All right, you should be getting a number that is relatively small and slightly south of 4. How do you do the square? Is it 1 here? I don't know. It's really not. Should be bigger. Yes. All right, you should be getting 3 point something if you are not. 3 point something.
If you like don't have proper notation on multiple choice, doesn't matter.
They just see a Sandron. Cool. What did I do? Oh, silly goose.
Okay, now I got it.
All right. So they are big fans for some reason. I don't really get it of making these functions really gross. So just take your time when you're plugging into the calculator, because this question, in essence, if I know how to integrate in polar, this is not a hard question. So we just need to make sure we take the time and don't lose that answer point. Please do show your setup though. So this one is 3.534 since we're always given our 3 decimal places. So 3.534. So these are what most of the free responses look like. They're very explicit about what area you're looking for and what bounds you have. I was perusing some of the multiple choice and they were a little less explicit. So we're going to use the calculator and kind of some of our knowledge to be able to help us with finding something like this. So we are going to find the area of the region bounded by this graph. What is kind of glaringly missing from this problem, though? Bounds. So we need to figure out what we think the bounds are. Now, you can think like the unit circle, and you can verify on your calculator. Keep in mind that this angle is always theta equals 0. So how far does it look like it takes this guy to get from this point all the way back around if you're thinking in angles? Just 180 degrees. It looks like it's taking 360 degrees. So what do you think the bounds are if we're going to be working in radians? I would think 0 to 2 pi, because it's taking kind of like the unit circle, it's just taking a little bit of a different path. It's taking the full way to get kind of the full circle to get all the way around. And most shapes we work with will be 0 to 2 pi. But if we want, we can do this on the calculator. So I'm going to show you how to graph in Polar. It's not super necessary for the AP test. There's lots of ways to work around it, but it can give you some good visuals if you like. So pick up that calculator and press mode. What do you think I'm going to change? Oh, I'm staying in radians. I'm going to go down, and instead of function, I'm going to grab polar. Yeah, want to be really uncomfortable? Press Y equals. Now it says R equals. Also, anytime you press X, hello, theta. All right. So what I'm going to do is I'm going to plug in 2 plus 2. Yeah, did anyone ever wonder why the X button had like X, T, theta, N? It's because you can get... You got to change your mode. All right, let me zoom. All right, so the zoom can be a little bit weird. So if you want to get yours back to the normal menu, your calculator screen is a little more rectangular than square. So if you press zoom 6 like the normal standard window, it's kind of flattening your shape a little bit. So if you want to get a realistic view, you can do zoom square, which is number 5. That'll get you kind of this rounded shape that we can see, and you can still zoom in and zoom out. Now, how could I confirm that this is taking from 0 to 2 pi? My favorite button, trace, still does a great job. So it's telling me what theta I'm at and what X and Y value I'm at, which is kind of cool. As I trace along, it's changing the value of theta. So I'm moving to the right, it's changing theta. Notice here that when I get right here, what's that theta value? 3.141592. That's pi. So 180 degrees or pi radians. I've gone halfway around that shape. You want a polar part too? Oh. Actually stays. Did you run yesterday and I just missed it, or did? I know. It was really late. I was choosing the graduation speaker. I'm sorry.
Who is it?
It's not announced yet.
Bye, Mason.
Bye, Mason.
Oh, who is it?
Probably next week. Maybe. I don't know. I can't tell.
Nate, is it
Can't tell you.
That could be a week.
All right. So there is pi. If we keep going around, there's 3 pi over 2. And this guy is 2. I press trace and I'm just using the arrows. All right. For trace, you can also plug in numbers. So I could plug in some of the other numbers. I could see where I'm at pi over 4. Just keep in mind for trace for polar, you're always at an angle. Now there's other ways to confirm this as well. If you go to window, the window now looks a little bit creepy. You can, because polar kind of will keep revolving and doing points, you have a starting and stopping value of your thetas. So this is graphing from 0 to 2 pi, and I saw the whole shape. But if I change it to like 0 to pi and press graph, you'll notice that it's only graphing that top part there. So a bunch of ways to confirm that what you're seeing is actually what you want. So 2 pi, I will put it back to so we can see the whole thing. All right, so not surprisingly, hopefully, our bounds are going to be 0 to 2 pi. And most of the time, if you are looking for bounds, those are pretty good ones to choose, especially for shapes like limacons. Anything that looks like it's kind of doing the full workaround is a great shape to choose. So I'm going to do 0 to 2 pi. What will my integrand look like? 1/2 Cool. Let's see if we can all plug that in. I'm just going to trust you guys when you tell me a number. So please make it right. I actually lied. I have the number on my paper. So 850. Yeah. I don't like the 0 at the end. Makes me it's science to round it. Sig figs are the worst. Can you imagine if on top of all the calculus I had to teach you about sig figs? That would be the worst. No. Sig figs are always 3 for us. No, 3 decimal places. That's all you need to know. All right, before we move on to the next question, I think I'm going to do 2 more after this before we take our break. I want to start pointing out that, especially for multiple choice questions, they like to get a little creepy with multiple choice, that there are ways to do polar area where it's a little bit creepier because you're taking advantage of the symmetry. So would you agree with me that this side of the graph and the right side of the graph look like they're the same size? So I could actually do this by taking half of the area and just doubling it. So I could do 2 times the area of 1/2 plus 2 sine theta squared. But what would my bounds be? Let's think of that unit circle again. We're going from straight up to straight down. 0 to pi would be from here to here. Good idea, though. Pi over 2 would be a great bottom bound. And 3 pi over 2. Yeah, so if you have a shape that kind of goes just out, it doesn't like come back in. So it's not one like these. 0 to 2 pi is generally what you're thinking of, just like the unit circle. So I only point that out because they really like doing this in multiple choice questions because they think you're going to drop the 1/2. So they like to craft the bounds so that they can create an integral that also doesn't have a 1/2 to get you confused, essentially. So just keep in mind, especially for multiple choice, that they may be a little crafty with their bounds and they may not just go from 0 to 2 pi. So speaking of crafty with our bounds, we're going to try the next 2. These are kind of the biggest focus on bounds because the roses seem to come up in multiple choice a lot. So we're going to do 2 different ones. We're going to look at the graphs a little bit first, though, because these are a little fun and funky. So, yes, after we do these 2 questions. We're almost done. All right, so I just want to show you what these roses do. Again, the graphing stuff is not in general something that you have to know to be able to do these questions right on the AP test. They're going to give you a graph or allow you to use a calculator. They're not testing if you know what 2 sine 3 theta is, but I think they're cute and fun to look at. That's not how you spell theta. There we go. I'm just going to add some sliders and mess around with them a little bit. Everyone excited for the basketball game?
Yes. Are you playing in it?
Heck no. That would be embarrassing. Shuddy is. Luttrell is.
Yeah, Dr. Luttrell is.
Yep.
Oh, that's she play basketball.
Oh, that's
Yeah.
good.
Oh, it's because I saw that, but I saw like this map and it was like all the graphs of like all these flowers, and it was like going up for like 10 petals, and then back.
Yeah,
like,
it's really cool. So all of the ones for all of the ones that look like this, that kind of have petals going out, they're called roses. They all have a number times either sine or cosine, and then a number times theta. I just want to do a real quick number talk, if you will. What do these 2 numbers do? So what do you think the A is doing?
making it bigger.
Yeah, it's essentially giving us the length of the petal. So each of those petals is a certain amount long. It's a little easier to see with cosine. And if I change, it's kind of the length of the petals. Let me see if I can give you some steps here to look at. So notice right now my A is 9. Look from the pole out to the right-hand side. You're looking at a distance of 9. It's a little easier to see with cosine because cosine ones are really symmetric towards the x-axis. Let's get down to a little bit of a smaller one.
Oh,
So we can see.
Sine
Sine versus cosine is more so where the petals are aligned. So the cosine ones always have one on the x-axis, and then the sine ones always have one that's like in the first quadrant. Again, not stuff that you really have to know at all, just kind of fun facts. Let's look at what the B does though, because this one's really interesting. Kind of. So Cheka said it's the number of petals, and I said kind of. Anyone see why I'm saying kind of?
But it goes back and forth between more and more.
Yeah, so it looks like odd and even are doing a really different thing here. And that's certainly true. For odd numbers, it's exactly the number of petals. What do you think it is for evens? Yeah, we would have double that number of petals. So if we have 6, there's 12 petals. If we have 5, there's 5. If we have 4, there's 8. Yes, it is. All right, Rashad asked a good question. Is that true for sine and cosine? Yes. So sine and cosine are more so just changing where the petals are located, which is pretty cool. So let's go back and look at more so these questions right here. Again, the thing that is kind of glaringly missing in this problem is the bounds. So for these ones, because these are the ones I think that are most likely to come up on a non-calculator part or on a multiple choice, I'm going to show you how to find these bounds by hand, but I'll show you how to check them on the calculator as well. One thing I noticed is that every petal, and the petal is like one of those loops. So we're going to try to find the area of one of these guys. Now, notice that when I drew that, I started and stopped at the pole. Yeah, the same place. What is the radius at the pole? All right, if the distance from the pole is the radius, 0. So to find this place, to find my start angle and stop angle, I'm going to go ahead and set r equal to 0. So I'm going to say 0 equals 2 sine of 3 theta. Now this is going to involve a little unit circle knowledge, but I'll show you how we can check it on the calculator as well. So I'm going to divide by 2. I don't know why I switched sides. Apologies if that makes you mad. And what I'm going to do is I'm going to try to find 2 consecutive angles. So 2 that are like there and then the next angle where the sine of that angle equals 0. So can you think of any angles where the sine of that angle equals 0? 0. And the next one would be pi. What's important about those 2 specifically is I'm not doing like 0 and 2 pi. That would actually give you 2 petals here. I want to choose 2 that are consecutive. Yes, but think of like sweeping out area. You'd be sweeping out too much, essentially. I'm going to divide by this 3 to get 0 and pi over 3. Now that set of angles there is actually going to get me specifically this green petal, but I could also have chosen like pi and 2 pi to go from pi over 3 to 2 pi over 3, and that would give me actually this petal down here. So you just have to make sure you're choosing 2 that are right next to each other. Yeah.
Are the problems ever going to make you have to find all the petals?
Well, think about, you could find this petal and then multiply by 3.
Oh.
So the symmetry in this case could be really, really helpful because then I wouldn't have to deal with it. All right. So let's go ahead and set up this area. I'm going to now go from 0 to pi over 3. And what will my integrand look like? Okay, I'm going to start putting the 1/2 out front because that makes me feel better. Perfect. Am I done? Yes. In this case, I am. A lot of these integrals are going to involve a singular trig function squared, so like sine squared. You actually can't integrate that without what's called a half angle formula, I think. So you need quite a bit of pre-cal knowledge to be able to do that. So for most of these, you're just going to be able to set it up and forget it. But again, I could certainly make this a different set of angles. I could go from pi over 3 to 2 pi over 3. If I were playing around on my calculator, you might notice that this whole shape takes only from 0 to pi to make. So you could do 0 to pi and then divide by 3. The symmetry can be a little wild, but it can be really helpful if I want to just think of either a small shape, big shape, part of a shape to simplify my thinking. Charlotte. To get from here to here. So I was looking at pretending like this was just like a singular function here. I was thinking sine of what will get me 0. Sine of 0 will get me 0. Sine of pi will get me 0. Thank you for making me re-explain because I didn't feel like I did a good job the first time. All right. Let's look at one more. Oh, wait. I was going to show you how that one shaded out. All right, so if you're looking at this one, it's going to do it in degrees. But if you notice, this is sweeping out the first petal. So we started at 0, and it's just over 60 degrees now, which is pi over 3 radians. So you'll notice I have the first petal here, and then it keeps going. Now, you might notice there's 2 different colors. Anyone think they know why? Yeah, the radius being positive or negative. Now notice as I'm going out to 2 pi, this one is actually tracing over itself twice because it only takes, for the odd number ones, it only takes 180 degrees or pi radians to get all the way around the shape. But again, if you're kind of just solving and using those 2 consecutive angles, you don't really have to know that much about the shape. You just need to be able to figure out which 2 consecutive angles will get you back to the pole. I think it's a little calming to look at, you know? And we're doing 4 theta now. Yeah, they get kind of wild because you can, it like goes across a lot. Whee!
I don't really like how the odd numbered ones go.
They look a little funky sometimes.
Like, not like the even.
All right. Team odds and team evens. Good question. I actually don't know. Probably get really weird. And say it's undefined in some places, so it's just gonna go. Yeah. All right. Let's go ahead. Let's do you guys want to try the next one on your own? Or should we do it together? All right. Then you guys tell me what to do. What's my first step? I got this guy. I want to find 1 petal. All right. Radius equal to 0. Let's roll. Yeah, because the petals here are always coming back to the pole at their start and finish. And that radius equals 0 tells me where the pole is. So yes.
Wait, can we try to solve this on our own?
Sure. Yeah. Take a second. Try to solve this on your own. Try to find. Nice.
We're all just trying to educate ourselves.
All right. Again, you're trying to find 2 consecutive angles. I didn't divide by cosine. Why? I'm figuring out what angles did I plug into cosine to get cosine divide. I can't divide by this function. All right. So where is cosine 0 on the unit? Okay. What angle is that? Pi over 2 and 3 pi. So I'm going to put here. And then divide by 2. Yeah.
Well, that's just convenient, isn't it?
Mm-hmm. I think so. Yeah, it's really not. It's not terrible unit circle. What? Can you divide by 2 and not multiply by 2?
Oh.
Treated cosine equals 0. Pi over 2 is one place is cosine 0. Where's the other one? flip those numbers. You want down. All right. Hey y'all, where is cosine equal to 0? All right, 3 pi over 2 is one of them. Pi over 2 is another one. All right, I could choose a different set. So I could choose like 3 pi over 2 and 5 pi over 2. I could choose negative pi over 2. That's just going to get me the area of a different petal. It doesn't matter which one I choose. They're all the same size. If I knew how far it took to get around the whole thing, I could do that divided by 4. Get crazy. So I'm going to divide by 2 here. Oh, this is lagging. I'm going to get disconnected. All right, going to shove my front. And then my bounds here. Yeah, it's not too bad. If you kind of give up the fact that you don't have to know what the shape looks like, it does get a lot easier. Now, you could even get really crazy with the symmetry. I point out that you can do this if you want. What? Most of them are given to you, yes. Yeah, most of them are either given to you or you get a calculator and you can make it yourself. The last thing I wanted to just mention, symmetry-wise, do you agree with me that these petals are even symmetrical, like across the x-axis? Yeah. So if you want really crazy, you could even find like half of a petal if you wanted to. This is theta equals 0, so I could go from like 0 to pi over 4 this first place back. Keep in mind that symmetry can be very, very cool in these cases, and it can allow you to do a lot of cool things. So we're going to take a break right here because this is a pretty natural break in the notes, because when we come back, what if there's 2 curves? If there's 2 curves, we actually have 2 different types of situations we can have. One that's like a top minus bottom, and then one where there's like one function working at a time. If that doesn't make any sense right now, don't worry. I'm going to teach you when we get back from break. Let's take 5. Sam. What? If I wanted to find half of it, yes. So what I was saying is if I found half and I wanted the whole one, I could multiply that by 2 to get the whole petal. So like for this one, if I were having trouble maybe finding the second angle here, I know that this is theta equals 0. So if I could just find pi over 4, that could allow me to get the area even if I can't trig all the way around the unit circle. Yes. Mm-hmm. Yeah. Just next week.
Next week is our exam.
I see. We close. Yeah. I think you guys are going to do really well. You just got to trust yourself.
How are you choosing partners? Or like, how are you choosing partners?
I don't know. How should we do it?
Choice.
I don't know. Some of you guys might choose wrong. Who would you choose? Mm.
I mean, if you get the produce for that, might still match up.
I think so.
So you all have really good grades. So it's like honestly, the grades is like a toss up. It's almost like doing it randomly.
Are we allowed to just guess?
What do you mean? Oh, like if you have a calculator? Yeah.
Like if you can see it.
Yeah, if you can see it. I think these ones are a little bit harder because it only takes pi to get around. But yeah, if you think you're right, what you can do on the calculator is kind of check, kind of do trace and plug in some angles to check. That would be the way I would do it.
There's like 4 things, so it's just 1/4 of the way around.
Yeah, that makes sense to me.
Also, you said like it's symmetrical, so you could do that. Could you do like that half of that one and half of that one? Like you could just go from 0.
Yeah, you just have to make sure you know kind of what bounds you're working with. I think that you're right that the even ones are a lot easier to kind of finagle that way.
Yeah.
So this one's definitely a little bit easier than some of the other ones. Yeah, so 0 to pi should work, or 0 to pi? Pi over 2 should be working the same.
And then are the reasons the odd ones like only do that? Is it because it like goes around twice?
Yes. I haven't like thought of graphs as
I
from
just
like a
think these are
graphing
super
perspective.
cool.
They are. They're super cool
Also,
looking.
it's how I draw like flowers,
Oh,
like
nice.
just automatically.
Yeah, I think the graphs are super cool, and I wish I need one of these years make sure I build in more time to talking about the graphs, especially because only math analysis does them. Like you don't do them in pre-cal at all.
Remember any of that?
Yeah, but at least you get time to investigate the graphs because they are very, very cool, and there's so many patterns, which is nice.
Yeah. Math can be cool.
Yeah, it really can. It's very cool.
I gotta switch controllers for the. I would play it at 30. It's just $70.
How much did you pay? Why
One,
not? But you think that's a little suspicious?
it's untested, so gambling. But okay, here's that. It's untested. Okay, you probably doesn't switch. Just hold on.
Why not? It's crazy.
Sure, Beg for it.
How can I sell my name?
You're the older. No, it's not really.
Okay.
From danger. First time he went, I think maybe your mom or grandma. No. He went through a video. He was flexing to me. He won. For the first thing,
Yeah, I was looking at my phone all the time, so I'm like, you know, I'm gonna last
All right, let's roll. The quicker we go, the more time you get on this notes check at the end. Speaking of the notes check, this next question is almost identical to the question on the notes check, which is a little bit helpful. I tried to structure this one so they look similar. So let's look at it. We have to set up an integral that will give us the area inside 3 sine theta and outside 2 minus sine theta. Now, I want to see if we can figure this out before we kind of look at our calculator. They have graphed these for us, but they have not told us which graph is which. I want you to think about the complexity of the two functions, I shouldn't use the word functions, the two equations that they're giving us, because these aren't functions, they don't pass the vertical line test. Look at the complexity of these two equations and look at the complexity of the look at some of the numbers involved in the functions and some of the numbers involved in the shapes. And I want you to make a prediction with your table. Which one do you think is which? Take about 30 seconds to talk, and then I will ask you. Aw. All right. What do you think? Which one's the green one?
2 minus sine.
Ooh, we have an argument. You think 3 sine? The blue one? Oh. What graph are you looking at? Okay. All right, so let's talk about ways we can think about it. One way you can think about it, you could start plugging in some angles to help you out. So let's like plug in, I don't know, let's plug in 0. What's 3 sine of 0? 0. So like there. And what is 2 minus sine of 0? 2. So like there. So I could look at plugging in an angle. Also, the number sign or number cosine, those are actually always going to be circles, with the 3 representing kind of the diameter of that circle. So there are a lot of ways. You could certainly graph this on your calculator. You're going to get a calculator for most, if not all, of your polar questions. But plugging in some angles or just kind of looking at some patterns may help you out. The 1 minus these guys, or number minus a trig function, is always going to give us some version of a limacon, which kind of looks, depending on how deformed, like a deformed circle. So, all right. The other thing they give us in the question, which seems to be a relative theme with questions now on the AP exam, is they're giving you these 2 intersection points. Now, we could certainly find those on our own by setting these 2 functions equal to each other and solving that trig kind of just the same way we did before. It wouldn't be too difficult to find these, but it seems like recently they've been giving you those intersection points. So to find those, we could solve this equation. Now, let's talk about which area we're actually trying to find. So we're trying to find the area inside of 3 sine theta, which is the circle, but outside 2 minus sine theta, which is that kind of purple Lemus graph. So would you agree with me that I am trying to find this area in here? Okay. Cool. Now, what the radius is. The radius is the distance from our pole out to whatever graph we're going on. Here, notice purple graph is in between the green graph and the pole, no matter where we are. So as I sweep out my arm using kind of my elbow as the anchor, there are always 2 functions touching my arm. Yes, one is on the outside, one is on the inside. So this is very similar to a problem that we called like top and bottom, where we had a top function minus a bottom function. Top and bottom gets a little weird because top is just like far away and bottom is right there. So this, we are going to be subtracting our 2 sector areas. So let's talk about what this is going to look like when we set it up. I'm going to only keep my 1/2 outside of my integral. And I'm going to do my top function minus my bottom function. Which one is the top function? 3 sine theta. We're talking what is farthest from the pole. And then my bottom will be what is closest from the pole. All right. Reading my mind, bounds would definitely be pi over 6 and 5 pi over 6. And then I did something really, really wrong on purpose, and I want you to tell me what it is. I didn't square it. So these have to be squared, and they have to be squared individually. If you think about the area that we're finding, we're really doing sector minus sector and not squaring the distance between those 2 curves like we would when we were just subtracting the area in rectangular coordinates. All right. Am I done? Set up, yes. Again, a lot of these questions are just going to be set up and not evaluate, because that is not something that with our skills this year is integrable. Okay, so think of we want to, for the top function, we want the bigger r, and for the bottom function, we want the smaller r, because when I subtract, I want this to be a positive number. So I'm choosing the function that is farther from the pole and the function that is closer to the pole. So since this distance, this r is bigger than this distance, and that's true the entire time, right? Yeah. Even if I go over here, this one's farther than this one is.
Oh, no, I mean, like how you knew the top of the 3 sides.
Oh, okay. I apologize. Wrong question. Yes. Mm-hmm. So a couple of ways you can figure it out. We could use our calculator and graph it. The 3 sine and 3 cosine, all of those kind of things are always going to be circles, but you can plug in points. I think that's the easiest way to verify. So let me choose a different angle than I did before. Let's say I plug in pi over 2. 3 sine of pi over 2. Sine of pi over 2, I believe, is 1. So that's 3. Pi over 2 is this angle up here. So that's at 3 there. As my radius here, if I did 2 minus sine of pi over 2. Yes. So you're looking for wherever that point would be. So this would be 2 minus 1. That's 1. So that one's on the purple one. So it's just like if you had graphs and you were like plugging in an x and checking the y, you're plugging in a theta and checking the r. Mm-hmm. Cool. All right. Type number. Oh, we have this one. What time is it? We're going to skip this one. Let's look at this guy. This is one of my favorite questions. All right. Let's figure out what area this is asking for. And then I'm going to ask you why the green line is there. The green line is there for a very specific reason. And it's in that specific place for that reason. It will have to do with the bounds, yes. All right. So let's look at, first of all, try to figure out, again, which function is which. I'm going to give you a couple of seconds to try to figure out which one is which. All right, which one's the red one? All right, and then this guy is then 1 plus cosine theta. If these numbers are equal, the number there and the number in front of cosine, that's when we get this like butt crack, if you will. A cusp. All right, let's look at this shape. Again, we're going to try to make sure we know what area they are talking about. So I want you to talk with your neighbors. What area is the common interior of both of these? To help you out, I would kind of think like a Venn diagram. Think common interior is like the spot where they overlap in the middle. Can you try to lightly shade that on your paper? Where is the common interior of both of these shapes? It should be pretty big. All right. Are you guys shading like this part? Yeah. Okay. I'm going to tell you symmetry is going to be helpful in this problem. It may not seem like it at the beginning. We'll do the problem and then kind of reflect at the end. But would you agree that the stuff above the x-axis that I shaded yellow and the stuff below the x-axis that I shaded yellow are the same size? So we're going to focus on the top part. Nazi. So the dotted line is going to help us, yes. So the area that I'm talking about is this. I'm going to color code a little bit to help us out. This. And I'm going to cut it here and end up multiplying by 2. Okay? All right. I color coded a little bit to help us out with what I'm going to ask you next. The question is, why is the green line there? Okay, something definitely changes at that green line. Let's look. I want you to answer the question, how many of my polar curves that have to do with this area is my arm touch? So I'm at this one. Am I touching both of the curves when it comes to like between this and the pole? Oh, whoa. Whoa. Am I touching both the curves? Yeah. Sorry, just the area that I want. Oh, my hands are too long? No. I'm touching blue, 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 blue.
Oh,
blue,
it's where the common area
red, red. Oh. So I would argue this question is a lot different than this question. Because here I was touching green, purple, green, purple, green, purple the entire time. But here, I actually have a situation where this, so is there a way to make it less? I don't think it likes one note. I would argue that from here, this sector has everything to do with the blue curve and nothing to do with the red curve. This little piece has everything to do with the red curve and nothing to do with the blue curve. So we're going to split this into 2 integrals, one that has to do with blue and one that has to do with red. Yes. Because of what we talked about with the common interior. I know that I am looking for this part, so I do have to investigate which part first, because if we were working with like this part of the graph, then I'd be touching red. Yeah. So it's going to depend on what part of the area we want.
So it's just start to the pole and it goes to the edge of the common.
Yes, exactly. Good vocab.
You know it's that because it's. How do you know it's only that part? Like,
So we found that we wanted the common interior. So I know I want this part in here.
yeah.
So as I go from the pole out to the edge of that area, notice I'm stopping at the blue and then I'm stopping at the red.
One half is easier.
Mhm. Yes. So since I'm going to have to split this into two different shapes here, so I'm going to have to do kind of that red shape and that blue shape, I'd like to not do that again.
Oh, so you're just.
So that's why I'm doing the half.
Okay, thank you.
Absolutely. Good questions, y'all. All right, so let's get focusing on setting up some of this stuff. So I know I'm going to have two integrals. I'm writing this at the bottom just because it's going to be a little long. One is going to be talking about the 1 plus cosine theta. That's our blue graph squared. And then the other graph is going to be talking about, what was this guy? 3 cosine theta.
Does the order matter?
No, because I am adding them together, so it doesn't matter at all. I'm doing them kind of in a chronological order based on the angle, if you will, since 0 starts right here.
Is the reason that we did 2 different integrals?
Yes. So unlike the last one, I could have done 2 different integrals here if I wanted to, but since they have the same bounds, we can put them together. Absolutely, since they have different bounds, I have to do 2 different integrals. All right. Let's focus on the blue part right here. Anyone think they know the bottom bound of the blue part? 0. We're going to start at that angle 0. But now I need to figure out, where is this green line? Let's see who's been listening. How could I find this spot where those graphs intersect? Set them equal to each other. Let's do this by hand just to see if we can. What would you do first? Common denominator. Combine like terms. There we go. It's like, where are the fractions? All right, I'm going to divide by 2. And now I don't need 2 angles here. I just need 1 angle. I notice it's in the first quadrant. So I really want to know, where does cosine equal 1/2 in the first quadrant? If you're thinking about what angle you think it is, it looks like that angle. So because we're just looking for this one spot right here. I think it is 2. All right. So if that top bound is pi over 3 in the 1 plus cosine integral, what do you think, where do you think pi over 3 is going to go in the next integral? Bottom bound. We're picking up at pi over 3. And then how far are we going? How can we figure it out if we don't know? All right. What's equal to 0 at that point? All right. That was a really terrible question to ask. How can I ask this better? If I want to figure out where that point is, I could take the red graph, which is our 3 cosine theta, and he's at the pole right there, right? So what's the radius at that place? 0. So to find this point, I could set this equal to 0. Where is cosine theta equal to 0? Pi over 2. Cool. It is a little confusing because actually these 2 graphs are reaching that point at different angles. So it gets a little bit weird. But anytime you're at the pole, if you want to know what angle you're at, you can always set that equal to 0 because our radius is there. All right. Why is my answer currently wrong? Yeah, you could cancel the 1/2. Again, I kind of talked with Hannah up here about it, but going back to the reason I chose to do just above the x-axis here and use symmetry, I noticed that if I were doing this question, I was going to have to break it as I went. I kind of don't want to do that again in the bottom half of this graph. So that's why I found it very advantageous to just do the top half and not worry about the bottom half. So it was definitely a choice on my part. You can do this question with the top and the bottom, but why do double work when you can just multiply by 2? All right, last question. Looks crazy, doesn't it? Really? Okay. This is a real AP question from 2017, and this is pretty far down in the free response. So you can kind of tell it's an AP question because of the amount of words. It's a little scary. So let's look at this question. I believe it was a non-calc. Oh, maybe not. I can't remember. But actually not too scary. So the first paragraph is just talking about this graph. Let's see if we can figure out, oh, it definitely was a calculator question because of this function. Looking at this, does anyone think they know which function is which? Oh, it does? Nice. I didn't read that far. All right. Which one is which?
The R is the first one.
Oh, nice. It does look more complicated, and this looks like a more complicated graph. So I'm going to roll with what you guys are telling me. Yeah, if you ever need any more information, just read. But you did have a calculator for this question, so you could also figure that out that way. Now, again, a lot of this stuff is similar questions that you could be asked to like A/B style questions. This type of question seems to be getting asked a lot. I've seen it on a few recent AP exams where they have something going on where you are wanting to split this into 2 equal pieces. So this ray that they're talking about, theta equals k, it's theta equals some specific angle the entire time. So that's like taking a line and slicing this right down the middle. Thank you. Oh, it looks much better up there than it is here. Nice. Okay, so we're trying to divide this into 2 regions of equal area. What do you think? This is a vague question. I'm hoping for a specific answer. What do you think theta equals k is going to function as in my expression involving integrals? A bound. That's definitely going to be at least one of the bounds in my question. So we're going to write probably 2 integrals where if we set them equal to each other and make an equation, that equation would allow us to find k. We don't actually have to do it. We're just setting up that equation. But this type of question of saying, hey, slice this in half and show me an equation that I could solve seems to be relatively popular. So let's do it. All right. So is this situation where one curve takes over after the other curve? Or is it this situation where we need to do top minus bottom? Everyone's pointing at this one. Good eyes. All right. If you need an elbow rotate demonstration, look, I'm touching both G and F, G and F, G and F the entire time I'm going around. So let's set up some integrals. I'm gonna pull 1/2. I want to work on this part first. What are the bounds of that part? Where do we start and stop? 0. Okay. We're not going to get all the way up to pi over 2. If we were trying to find this entire shape, yes, absolutely pi over 2. I'm going to stop at k because I want to just do half of it. What is my integrand going to look like? All right, top minus bottom. So I think, which one's top? G, it's farther out, minus bottom. So this is all good. This is right. Squared. Nice. Okay. What do you guys want to set it equal to? See the other one? What do you mean the other one? All right, so what I've set up here is like this part. Yeah, so k to the next point, essentially. So this integral, do you agree that the top and the bottom functions are exactly the same still? Okay, so just kind of annoying to rewrite. I'm not going to write an x. What is that? Theta for the win. Same exact thing. And Rashad's claiming the bounds k to pi over 2. Yeah, like pretty much it tells me the entire thing. So why did we write that? So they're saying write an equation that tells me where I can slice this thing in half. So I want the bottom half, that is this integral, so that's this stuff right here, to be equal to this top half, which would be this integral going from k to pi over 2. There are other ways to do this, certainly. I could say that this first guy times 2 is all the way from 0 to pi over 2. That's perfectly fine as well. Lots of ways to write this equation. This happens to be the way that my brain thinks about it. I think I have all the squareds I need, right? Oh, I didn't square the whole thing. I multiplied it all by 2 because I just found the top half. All right, you guys want to be done? All right, end notes.
Wait, we're not making that?
No, that's it. That's it. We done. All right, but you are not done for today. You owe me a note check. The note check that I am going to give you. First question. Looks a lot like this guy. Second and third questions are from out of our last video, so you may want to point 3 out.
Hey, Justin.
Yep. I will tell you, the one that I'm giving you is a real AP test question. So this is about the difficulty level that you're thinking of. I think this is really accessible. If you can get the basics of polar down, I think you guys have a very good chance of scoring on high on the free response about polar. Remember, there's usually one that's either polar or parametric. Parametric is usually not super difficult. So polar is the one we want to make sure we have at least a basic response on. So good luck. Call me over if you need it. We have until 2:09. Yeah, so this was one. I think I was. Yes,
Now we're doing
technically, the one I'm giving you right now is non-calculator.
But
All right, I will be collecting this before you leave. Yes, I will put some dates up on the board.
Round 2 on the other objective, or whatever it is.
Yes, I think I got home way later than I was anticipating last night, so I think I forgot to read them, but I will have them next time for you.
10.3 and 10.4.
Yeah, you could do the first question first, and then
The first one's like
the first one's like what we just did.
like the one we just
Uh,
was like this one,
The
or this one?
I would turn over. I would do that one. Mhm.